the antiderivative. We talked about integrals where we're going from something like x cubed dx, and we're going to take the antiderivative. And we discussed that the rule contra pop down, power down with antiderivative was, remember, power up, divide up. So you've got your x to the 4th over 4. But where we finished at that point? You got to put the plus c, plus that constant of integration. All right. Today we'll look at some different problems, but that's essentially the same. I mean, I guess we could. What if we had the integral of x to the 1/2? Same thing. So that would be x to the 3/2 divided by
3/2.
Divided by 3/2. Let's see. Now, to simplify that, anytime you have a fraction of fractions here, we can write that x to the 3/2 here, but then instead of dividing by 3/2, we can multiply it by the reciprocal. And I'll put that reciprocal up front here, so multiply it by 2/3. Let's see. We'll do some problems like that. We also talked about this plus c creates a family of antiderivative functions, so to speak, all shifted vertically in different alignments. If you look there on top of page 324, we've got the constant multiple rule, and we've got the sum rule for integrals or for indefinite integrals, and they've got some examples there. Over on the next page, on 325, there's a little table 4.9, the indefinite integrals of trigonometric functions. So before we talked about how the derivative of sine was cosine, so that would mean that the antiderivative of cosine is equal to sine plus c. Yeah. The derivative of cosine was negative sine. So if I wanted to, I could put the antiderivative of negative sine, but nobody ever puts that. They write the antiderivative of sine is equal to negative cosine x. Let's see. And the way you can check that is if you think about it, what's the derivative of cosine? Negative sine. And so if we've got a positive sign in here, then that must mean that we have a negative out front here. Okay? So looking at that table, look on the right side. So you've got the integral of secant squared is tangent x plus c. The integral of cosecant squared x, negative cotangent. The integral of secant x tangent x is secant, and the integral of cosecant x cotangent is negative cosecant. All right? And I think that's enough. Let's go ahead and look at today's homework. I'll let you pick a few problems for us to work together, and I'll give you the rest of the class to take care of those. All right, so taking all requests, let's look at those. Which one would you all like to work together here? All right, let's go ahead and pick one there. Number two, you got it.
Is there any chance I could speak to her for just a second? I'm talking like 20 seconds.
Yeah, go for it. Figure out time.
Sorry.
We'll have someone pick another one here. Ivan, which one do you like?
Number 7.
Number 7. Alright, I guess we really haven't talked about how to deal with stuff in the denominator, but could you rewrite this such that that is in the numerator?
Would it be like to the negative 4?
Mm-hmm. So the integral of negative 9x to the negative 4 dx. So if you remember what's going on there, if you wanted to pull out the negative 9, you could. You know, write this as negative 9 times the integral of negative, or x to the negative 4 dx. That's the constant multiple rule. And then we can just write negative 9 times, let's go ahead and apply. Power up, so we have x to the
Negative 3.
x to negative 3.
Thank you, Mr. Potter.
You bet. And then divide up. So divide by negative 3. And then put plus c. Hardly all you missed was that I chose a mean one here with the x in the denominator. But we can pull stuff from the denominator up to the numerator when we put a negative exponent. Which we'll do about that. At this point, it's just, and then sometimes students make a mistake when they do the antiderivative because you see like the negative 4 and then they say like negative 5, you know, because we're used to go powering down. But we just have to remember that if you add 1, you know, negative 4 plus 1 is negative 3. Anyway, so negative and negative, that's going to be positive. 9 over 3 is 3, so we have 3. And then my answer key is actually going to get rid of negative exponents when possible. So you have 3 in the numerator, x to the 3rd in the denominator, plus c. That's it. Now, Ivan, what's the difference between number 7 and number 8?
There's multiple fractions.
Right. And if you remember, the sum and difference property of integrals said you can literally just take the antiderivative of this, take the antiderivative of this, take the antiderivative of this. So it's basically number 7 3 times.
Mm-hmm.
That's no big deal. Harley, let's go back and look at number 2, because you had questions about that, right?
Yeah,
Yep, that's fine. Well, that's what I wanted to be able to do. So this is the same kind of thing we mentioned yesterday, that you if you have the integral of several things, you know, like a polynomial, you can literally just take the antiderivative of each part. Okay? And so this 6 is a constant multiple, so we can just write 6. And then we have x to the 5th. So power up, that turns into x to the 6th over 6, plus, keep the 4, x, we'll power up that 3 to a 4 and then divide by 4. Plus, we'll keep the 9. X, power up that 2, we've got a 3 over 3. And always the plus c. At this point then we gotta notice we can reduce. So x to the 6th plus x to the 4th plus 3x cubed plus c. James, how can we check our work on these problems?
Take the derivative.
Yep. And take the derivative and see if it matches the integrand. If it does, you're in business. If not, check yourself. Alright, let's do a couple more here. Maybe one from the back. Gracie, you want to pick one there for us?
13.
She says 13. I say triple threat. Alright. Now you may look at that and say, Mr. Goddard, you never told us how to take the integral of stuff with cube roots and fifth roots and fourth roots. When I say remember your pre-calculus, Ivan, how can we write, I'll write that 5 there. How can I rewrite x squared cube root?
X to the 2/3.
X to the 2/3. Plus, that 28 over 5, I'm just going to write that as a fraction coefficient there. James, how can I rewrite the 5th root of x squared?
X to the 2/5.
And Gracie, how can I rewrite the 4th root of x?
Excellent.
Yep. You all know what we're doing here. So constant multiple rule, keep the 5/3 out front, times x. We're gonna need all our fraction skills here. What is 2/3 plus 1?
5/3.
It is 5/3. If you're not sure, use a calculator. Or, right, plus 1, which is 3/3. So 2 plus 3, okay, got it. Then obviously divide by 5/3. Plus 28/5 times the x. We're going to add 1 to the 2/5, which I'm going to write that as a common denominator as 5/5. So 2 plus 5 is 7/5 divided by 7/5. You can try to get fancy and not do this step right here and just multiply by the reciprocal, but you know what? I'm not that smart. I'm just going to do this step by step here. So 5/2 x to the, I want to power that up by 1, but the version of 1 that I want is 4/4. So I have x to the 5/4 and then divided by 5/4 plus c. And then I'll write this as 5/3 x to the 5/3. And then instead of saying divided by 5/3, I'm going to say times 3/5 plus 28/5 x to the 7/5. And then instead of saying divided by 7/5, I'm going to say times the reciprocal 5/7 plus 5/2 x to the 5/4, but instead of saying divided by 5/4, I'm going to say multiplied by 4/5. Don't forget your perennial plus c. And then just do some reduction here. 3's cancel, 5's cancel, so I just have x to the 5/3, that's nice. Plus 5's cancel, 28/7 is 4, so I have 4x to the 7/5. Plus 5's cancel, 4/2 is 2x to the 5/4 plus c. And that's my final answer. Sorry I didn't give you a whole lot of room there on that one. Feel free to use extra paper and staple it to the back. Any questions on that problem? Nope. Shall we choose a trig one? I say 21. So 21 is a little bit different. Harley, what's different about 21? It does have trig in the integrand. There's something else that's different about that one. Just a small difference.
It's dr instead of dx.
Yeah, it's dr. Big deal, right?
Mm-hmm.
Dr instead of dx. If you prefer looking at dx, then change r to x. Okay? It really doesn't matter. R is what we call a dummy variable. It's a placeholder. It could be anything. The most important thing, however, is that that variable is what is matched over here with the dr. Okay? If they were different variables, you'd have a different situation. So, also, I really don't like the way this sort of printed out. What this really is saying is it's the integral of cosecant r times cotangent r dr. So it's that's standalone, that's standalone. Just the formatting of and the way that it kind of renders on the screen and on the paper just makes it look weird. But this is cosecant r cotangent r. Okay. So constant multiple rule pulls up there. We can pull from memory or look at the table. What's the antiderivative of cosecant cotangent?
Negative cosecant.
Negative cosecant. Negative cosecant r plus c if you want to write this real nice and pretty, you could write -3 cosecant r plus c. All of these trig integrals, pretty straightforward. I'm not doing anything fancy. Next week we will talk about something called the U substitution method, which we'll get pretty fancy on. But for now, I just want to make sure we practice with straight up basics and definite integrals. Okay? Alright, so today we talked about applying all the stuff that we learned yesterday. We did some examples. Some examples with trig integrands, some examples with radical expressions, some examples with these, which I didn't do this, but we turn the radicals into these, which are rational, and just some straight up polynomials, and I guess these are rational with the denominator. But all right, shouldn't take you long to take care of that. And when you come back on Monday, we'll wrap up a little bit more on 4.9 and jump straight into 5.1. All right. Thanks for watching. James, go and kill that if you don't mind.